Just close this one. This one.
And you had
Okay.
a video, correct?
And I had a video.
So let's make sure that our cable is plugged in.
Oh, yeah.
And again, that will be controlled by your computer for just bringing up the sound. Everything else should be good here. So as long as your sound is at a level that you like, then it should be playing perfectly.
Okay. All right. Can you hear me? Okay. Well, welcome to EEC 290. This is the graduate seminar that I think many graduate students have signed up for. And I would like to say a few things about the seminar itself, how we're going to run it this fall. And then, since I will be the first speaker, I will start the presentation. So just 5 minutes about the seminar. Those of you who have registered, you should visit your Canvas and look at the seminar under EEC 290. And you will see that the seminar, you have to have a SU, satisfactory or unsatisfactory, that for those of you who have not been able to come to 50% of the lectures, you're going to get an unsatisfactory. Because what's the point of signing up and not coming? The second is there is another opportunity, however, knowing that you are all very busy and we are all humans and may not be able to come to one of these lectures. So these lectures, they will be online. They will be recorded and you will find them online. Now, the following, if you go through the lecture online, then you can, but you could not come here in person, then you're going to email me and say, I watched the lecture, I could not come, and I will put an attendance for you. Okay? Now, if you keep doing this all the time, I will know. So we can do it for special reasons and occasions. The other thing what I would like you to do is to submit after, you will have 5 days after the lecture, I would like you to submit 100 words. And you will see as an assignment, it asks very few questions. What did you think about the seminar? First of all, it's important at the end, it says, was your presentation well done? Was the presenter easy to understand? These are important, so we keep that in mind as part of the seminar series to make it better next time, all right? So this is like your feedback about every speaker. So that is part of your 100 words. And the other is, did this excite you in some ways? I mean, did you see something exciting in this presentation that made you, think a little more about some of your directions in your programs? So this is all. You're going to submit these. You have also the ability to miss 50% of those. But if you miss more than that, then we need to have a discussion. So that's how this is going to run. It's very easy for those of you who have access to Canvas. You should be able to see it all clearly. If you have any questions, email me. Yes? Of course, everything, online. I don't want paper. I don't want anything on my email. My email is already horribly long. Don't send me the 100 words through my email account. And also, if you read something from one of your colleagues, you can like it. Because if I find something really exciting, I will share it with all of you. So that's how it's going to go. This is a seminar to have fun, to learn, get excited about new things. I have given advice to all of the presenters to talk about the future as much as they talk about the present and some of them about the past. So I am the first lecturer for this, the first presenter. My name is Linda Katehi, and I'm a faculty member in electrical and computer engineering. I have been, this is my fourth institution. I came here as an administrator, not as a faculty. I mean, I was a faculty member at the same time, but I spent my first 7 years here as the chancellor. So it is now with really very excited to be back in the faculty. And what you will see is that I will speak about my own area, but thinking not so much, I will present, of course, things that I've done in the past to be able to make the connection, but I will talk more about the future as well, even if as I show things from the past. And all of this is under the umbrella, as you will see from the canvas, of the theme of this workshop, colloquium, which is the fourth industrial revolution, and specifically democratization of the information infrastructure. And I will explain why. Specifically, we'll talk about how to democratize everything that we design. So we design things for the broader public and not just for very few who can afford them, all right? And that's what our future, that's where the future goes. So with that, I would like, see, we'll have to test it. Okay. The outline, I will speak about the promises and the challenges of what people call the fourth industrial revolution, about what happens with technology acceleration and what are the social impacts of that. Of course, very clearly, the internet, the cloud, and the wireless grid that all of you have heard about or you are studying in your groups. And then I will focus on what I see as the wireless beyond 5G and the future of the RF front end. So this is my area of research. I am a circuit designer. I started looking at antennas as a graduate student, graduated from UCLA many years back. I moved from antennas to integrated circuits for high frequencies. I looked at high frequency effects. And eventually, over the years, I did work on RF front ends. So let me start by reminding everybody how many industrial revolutions so far, at least we all agree, or at least big part of the community, that we've had the first industrial revolution, which was water, power, and steam primarily. And that changed the world. It started in England. It changed a lot of things on how people lived and what kind of things they could do in life that they could not do before. The second one was with electricity, of course, and assembly lines. It started in the US. And with that, also, every time you have an industrial revolution, you have also a social change, and sometimes those social changes are so big that you have a social revolution that comes with it. And especially it has to do with labor and how then the labor force in that society where the technology changes everything that we do, how it is impacted, and therefore from grassroots up, the impact of technology forces some major social changes, and those we have seen, both of them, with the first and the second. The third one, which is the computer age, all right, the chip. I cannot say we had a social revolution, but we've had so huge changes in our life, and maybe you have not seen them, but I have, that practically I cannot even believe that I lived when I was young without the things that we have today. And I cannot imagine myself going back to this. And I also have to tell you that the environment we have created today with all of this technology is changing not just the way we work, it's changing the way we interact. Social media is changing the way society interacts, learns from each other, thinks about issues, and the way that we come together to request change. So with that, we are going to the fourth industrial revolution, which is what people are thinking is coming next. And why do we think that this progress that we have seen in technology is creating the beginnings of a new revolution? Because practically we are talking about totally changing the way we are and live as human beings. We will have so many implants in our body for good reasons, obviously, that will make us something different from what we were before. We will be able to extend life in ways we have not seen before. We are going to be able to change the way we live in ways we have not, and work in ways we have not seen before. Robotics. Many of you know it's a very hard area. Why is it hard? Because everybody wants robots for industry, especially manufacturing industry. And with artificial intelligence, not only they can do things better than humans in many ways, but they can think and make choices like humans within a space of choices and selections. And as artificial intelligence is moving forward, more and more of these robotic structures will behave like us, will work like us. But then there is a difference. They don't get sick, not as much as we do. They don't have families, so they don't have these responsibilities. When something goes away, you can just break it into pieces and do something else with that. And they can replace people in their jobs. So you can have a robot like this that can provide all kinds of services. And who are the people who were doing this before? This is happening within our own generation. It's happening within your own generation. I think I will see it too. And I'm much older than you are. And I think you're going to see beyond that, as a matter of fact. But the question is, what happens to the people? And not only that, but what happens in terms of energy we need to really keep them alive, if you use alive, working, when a medium-sized robot is requiring about the same energy like a human being. And when a human being is kicked out of his or her job, they don't stop living, all right? We have 7 billion people. We just have one more, not physical, not bio, but electronic, or we call it robotic structure that needs equal amount of energy. And where is this energy coming from? Nobody, I have not seen, I've looked around very carefully for all kinds of studies. No one. Everybody is doing projections for energy over the next 200 years without even taking into consideration how much more energy we need because of technology. So this is a problem. The way we work is going to change. The way we will be rewarded for work is going to change. The name work is going to change. So what do we mean by work? When a lot of what we call work today is going to be done by robots. And how are we going to then reward people in a decent way so we live as humans in societies that are peaceful? These are very important. We develop technology, we change our life without asking what this change is going to do to us as people. And it's important to start thinking about this right now. So you may have seen those, but these are 3 different graphs. The blue one shows, we're coming now more into electronics. The blue one shows how many numbers, so these massive interconnections, massive data, this is what we see. So $8 by megabyte, that was in 2004. Almost 0 in 2012. At the same time, from a few megabytes per second in 2004, we went to over 250. And at the same time, look at this, which is even more amazing, that we have almost exceeded 100 subscriptions for connections per 100 people. So we have more. Of course, that includes your Google connection, your regular email, your Facebook account, your LinkedIn account, your Instagram account, all right? Each one of them is a separate connection. It's not one. How many of you have more than one in this room? Almost everybody, with exception of some faculty, I have to say. So this is what's happening, all right? So who is going to be able to, address this kind of volume that is going, is exploding? Okay, beyond 5G, so now we are coming a little more away from robotic structures and the issues around them. That was just to trigger your thinking. But of course, when it comes to 5G or beyond 5G, we're talking about what people will call nano equipment. So for example, if we have so many subscriptions per individual, so we are coming now to have many more subscriptions eventually at some point than maybe the number of people on Earth. And all of these will require, therefore, nano equipment, the cloud computing, the IP platforms, and I'm not even talking about the energy that goes into each one of those. We have not even talked about this issue, right? So everything that we are doing so far, with exception of what we think is free, which is not really free, on internet, is not necessarily available to all people. So even if we will go to have almost 7 billion connections on Earth, it's not going to be at least one connection per person. There will be billions of people who will be outside of this grid, totally, not just the faculty. Billions of people who are younger than you are, who will have no access to this. And that is going to be a problem, socially speaking. All right, so going beyond 5G, I will focus on the access plane only, because that's where my area is, all right? So there are people who will divide that into 3 different planes. So I'm talking about the access plane, so the need for massive inputs and outputs, intelligent adaptive sensors, where you will have self-healing, so you will be able to fix any problems, hardware problems, self-charging, and self-organizing. So that's where the future goes. These are what we call interesting research problems in my area. And of course, carriers from millimeter waves to sub-millimeter waves. Low energy requirements, obviously, because if you have a sensor that is thrown somewhere in the middle of a jungle and you try to make measurements of the difference of temperature and humidity and so forth, you're not going to have a wire to connect it to an output. You're going to have a battery and you would like it to live as long as possible. And of course, architectural simplicity. So far as we add things, functions, as we add inputs, outputs, we only increase the complexity of the architecture. And I don't believe that can go for too long. So we need to start thinking about doing all of the above, but with simpler architectures, and of course, low cost. Because if we only focus on developing the X iPhone, how many people are going to be able to buy it? It's $1,000. There are people in other developed countries that make less than $1,000 a month. As a matter of fact, many of them. And so that's not what we are supposed to do as engineers, all right? Engineers is not just to develop things for the upper class. Engineers are supposed to change life for the better for everyone. So low cost is absolutely critical, and I don't believe we enter that into our thinking when we design circuits. Okay, future technologies for RF front ends. So If you look at an RF front end, for those of you who may have seen one, it's an antenna. You know, it's just what you have in your iPhone. You have an antenna, you have a low noise amplifier, and then you take your signal, you have a filter to clean it from noise, and then you down convert it once if the frequency of carrier is not very high, and then you go to digital and you do all of your work there. All right, and what you need out of the RF front end that is usually expensive as you go higher in frequency, the A to D converters also get more expensive as you go to higher frequencies. Everything becomes more expensive as you go to higher frequencies. And at the same time, you want to be smaller. Of course, it will be smaller because of frequency scaling, but then you want even smaller than that. You don't rely on scaling only to get small dimensions. You want the dimensions to go much faster because you have so many other things to put on your device. So many other sensors that have nothing to do with the RF front end. And so I think what you see in our area is that we have reached this level that I don't see much. I mean, we went like a saturation in terms of ideas and new things, and we stopped there. And the only thing was, how do I do the things that I'll show you, which I call, you know, the pre-5G. But then having done all of these things, what is left? All right? So maybe what is left is something totally new. Maybe a real-time adaptive hardware between the, after the antenna. Maybe dispersion-free antennas. What I mean by that is antennas where you don't care about dispersion. Because what we do with the RF front end, it's a very interesting. You design it for one frequency, for a few frequencies, and then you throw pulses at them. They have a very big frequency spectrum. And then, of course, what works well for one or a few frequencies does not work well for the other frequencies. You have all of these other problems that you need to get rid of. And then trying to get rid of the noise you get from all of these other, you know, the dispersion noise primarily, it's extremely expensive. So if you can get rid of this dispersion noise, would be great, isn't it? And then, of course, how about if you can do 1 and 2, then why not fully analog processing? The people tried to do fully analog processing many, many years ago, and of course it was too expensive because it was too difficult to get rid of the noise. And then, of course, it was much easier to go down to the digital and do everything. But now, going down to the digital, it's too costing in terms of energy. And as complexity increases, it has become even costlier. So neuromorphic RF front ends, why not? People are talking about neuromorphic computing. There are some concepts that can be brought to the RF front end. Let's see, in fact, whether this is possible. So these are the next few transparencies. So how do you prepare for the future? You have to build on what you've already done, all right? You cannot just dismiss everything that you've learned and move forward. And I wanted to show you some of the things that we've done in the past. So my work, since I will focus on that, started with the vision of the 80s when I was a young assistant professor. I'll tell you a story. I was on a plane and I was going to a conference. And there was this futurist. They invited this person. That was 1984. They invited this person, it was by my own society, to talk to us about the future. And I remember this person said, there is going to be a day, and I don't know when you're going to be on a plane, you're going to be able to connect to your florist and send, he looked at me, I was the only woman in the audience, he said, and send your husband a bouquet for his birthday. And we said, aha. What a nice future, you know? I mean, it was, and everybody laughed. That was in '84. And today, we do a lot more than that, is it not? Okay? So it has already, but that's how I started my work with the vision of the 80s. Then, of course, how would you be able to do that? By three-dimensional integration. You could not have antennas sticking out everywhere when you want to have something like my cell phone. You could not have, and that's how they were doing things at the time. There was no, it was not very easy to integrate And of course, three-dimensional integration became a way not only to integrate in one plane, but also in 3 dimensions, so you could reduce the size even further. Phased arrays for high gain, that was another thing. And then, of course, processing in the digital domain, that it was something that we've done for these systems. Specifically, for my work, we focused on, since 3-dimensional integration for the RF front end, and then this is an example of what we call the power cube that we did in my group. And I will show you a video that happens to be maybe 15 years old. I was able to find it as I was looking for it, because it shows how it shows, as a matter of fact, we designed that, but it shows what it would do. And I will start this video. And a student of mine at the time who started his own company was very nice to develop it, because I did not have the means to do that. And I will explain to you. Oops. So this is, the concept was to have these nanosatellites that you throw them without, like you throw them like a cloud, without any propulsion system. And as they go as a cloud, they find ways to reorient themselves and create a satellite with phased arrays, and who can communicate to a bigger satellite and then to a ground station. And that's what it shows. And also this is called the master cube. It's integrated. It has the top layer is all the higher frequency array. The lower layer, you will see later, is a lower frequency. So this in the beginning sends a unidirectional beam, and then identifies the others, which then say high gain beams, narrow beams, to be able to, and then they know where to arrange themselves. That was the idea, and to create a bigger antenna. Now NASA is doing some of these things now. They have this idea of throwing this dust of nanosatellites, and they are, because they're going away from the big satellites, which are hugely expensive. They live for this many years, and you're talking about $1 billion per satellite. So, and these ones are very inexpensive. You can have lots of them. A few of them can die. You don't even worry about it. And that's where NASA goes. But that started about 20 years ago, 25. So that's it. Oh, it shows how you can then, these are the traditional satellites. All right, so that's the past. All right, so that's the past in terms of research in my area. And how you were able to do this, very briefly, these were some ideas on how to integrate in 3 dimensions. How to do the designs. You can integrate homogeneous wafers, heterogeneous wafers, like this one. You can integrate, lines on different, and then connect them. You can have polymers. You can have chips. You can package them. I mean, this is what has already been done. You can use also like metamaterials to create very high Q filters without having a filter, but only having a substrate below the antenna. Then, 3-dimensional integration. That was exactly, in fact, that's the name of the micro machine cube. That's where it started. Why it is micro machine? Because in this particular case, because you have, for the first time, we developed vertical integrations through the wafer, and they worked better than any other vertical connection that had ever been done in much lower frequencies. So this allowed us to go to 94 gigahertz. When that was developed in the mid-2000s, it was for 94 gigahertz, it was for a radar application. But these are some integration schemes, all right? Everything on a wafer. And you can see here how you design all of the interconnections. Going from one wafer through another, up here you have different heterogeneous chips. This is a MEMS chip, this is a flip chip, varactor. you have an FET, and so forth. You integrate everything, you have a carrier substrate, and so forth. And that has been done. That is possible, it has been done now. It's already almost 10 years that this has matured. It's a mature technology for lots of industry. This, for example, here shows another way to integrate, excuse me, in this particular case, not only you use metamaterials, for example, you can use inductors that have a Q above 100. For those of you who do circuit design, an inductor printed on a substrate has a Q of 20. High resistivity silicon, 30. To be able to go above 100, because you need high Qs in the passives, if you are to develop a very small RF front end, you cannot have any more transmission lines to become your inductive elements, because they become too long. So everything has to be lumped. Lumped capacitors, lumped inductors. How do you do a lumped inductor when it has a Q of 30? So what you do is that you create something like this, which has a Q of 120. And that you can integrate like this. So all of these were things that we've done in the past. That shows integration from one, it shows an integration for a chip that lies on one substrate to another substrate. It shows integration between two chips. So from one substrate that has in this particular case was an indium phosphide chip, to another one that has a micromass inductor. And that shows the measurements for the various inductors. Transformers. You could never get a printed transformer to be better than 60% efficiency. And you were able to get to almost 90, 95 with these kinds. Of course, difficult structures to do, of course. All of these, you spend a lot of time to develop them, and they're not inexpensive, even if their quality is very high. That's another, you see here a CMOS chip that has been connected with another chip here, and then with an inductor on the ground. So all of this heterogeneous integration is critical. Okay, now we go to the future and ask the question, well, how much more can I do? Personally, when I started thinking about my research, I said, okay, we've done all of this. I'm not going to do and try to do a little more, a delta. Try to make, okay, the Q from 120 will make it 150. So what? The transformer will make it from 90%, 97%, okay? Big deal. It's not. So let's try to think totally differently about how we are going to do the RF front end. What happens today with your phones is that, oops, sorry, I went too fast. Oh. You get with your carrier. It is divided into subcarriers. It's turned into bits, all right? And then like pulses that have information. Is communicated because your carrier is frequency and creates an RF field and then can propagate. Otherwise, digital does not propagate, as you know. Your antenna receives it, so it's here. You do your mixing, low-pass filter, A to D, and that's it. But this one, it's very simplistic here, the way you see it. In reality, it does not look as simple as this. And if you want to do high frequency carriers, and if you want to have this to be fairly small and high quality and so forth, it's not going to, yes, you will have to play with these kinds of things, go one delta higher in what we've done in the past. And however, recently, people have started talking about hybrid digital analog, all right? So there have been a lot of papers that have talked about having analog here, processing up to some level, and then going down to your digital for processing. So at this point, I would like to show you some work that we've done recently. relatively recently that showed something very interesting. At the time when we did this, we had no idea of where this is going to go. It's just that we thought it's so unreasonable to have a time domain signal and to design your RF front end in the frequency domain. And especially to have narrow pulses and design your RF front end so it can only receive something very little out of the spectrum. And then you have all of these kinds of problems. So why do you even have to worry about the frequency? Why do you not try to develop a circuit like this where you have your incoming pulse with parity waveforms or incoming pulse? Usually for a communication system, your transmitter is a friendly transmitter. It's not like for radars, all right, where your transmitter may be a foe, so you don't know what is coming. But in wireless communications, you have information. So you can go through what we call a cognitive matching network. And why is it cognitive? Because it takes information out of the incoming pulse. And if you have a fast enough switch, fast enough, which means for our area it has to be sub-nanosecond, like picosecond type of switches, then you can rearrange your matching network so you eliminate most of the dispersion. And that's in this particular case what we published was your incoming pulse. This is what happened with the reflection, you know, with the conventional design. This is the conventional design where you have a matching network. Some of you remember that from undergraduate courses, all right? You have a load, your load can be your impedance. You have a matching network. The matching network is designed for a frequency. Then instead of one frequency, you send a pulse, and then it misbehaves. It misbehaves because it has not been designed for that pulse. It has been designed for only one frequency. However, by having this, you can really eliminate. Instead of having this to be delivered with all of this dispersion noise to be delivered to the load, you have really that to be delivered to the load. So there is another example. Same thing. You have a traditional matching network here, one with a switch, single pole, double throw switch, and an inductor. Obviously, you send this one here. This is what happens. Look, the reflection is as high almost as the incoming signal. However, when you go here, the reflection almost gets very small. And the other interesting thing that I wanted to see to appreciate that is that this is the bandwidth. If you try to think again about frequency domain, all right? And if you consider an LC simple, one-step matching network for the load, then a traditional matching network, LC, will have this kind of bandwidth, narrow. And what do you do to increase it? You put lots of these LC components. That's what you've learned from your simple circuit design course. With this one, your bandwidth goes like this. So practically, you have been able to allow all of the frequencies to go through just by not thinking about frequencies, but by doing your design in the time domain. If you decide to do a real time domain matching network, you don't think about frequencies anymore. And so let's see what happens with a real antenna, which is very interesting too. So you have a transmit antenna, a short loop, and then you send this pulse and then noise. Also, you may have another antenna that sends this noise. And this is a receive antenna where you have now placed a capacitor, a variable capacitor because you can vary it accordingly. Also, you have placed a switch, and this is your load. And what you see here is if this is your input signal, this is what you get at the load. So practically, you can see the peaks the way that they normally come. And even if you have to include noise in the system, and practically your input signal is 1, 0, 1, 0, so you are able to pick the peaks of these you don't care anymore. The ones are up, the zeros are down. You don't care anymore even about the amplitude of this peak as long as it is above noise. And then you can really find the bits of the incoming signal directly. Now, sorry. People will say, what happens if your signal is in your noise? Then you do correlation because you know what is coming. You have information about the incoming signal. And in this particular case, you could use correlation. And then you can bring your signal out of your noise. And that is also a well-known technique. So moving down, I would say what I became interested in was resistive switches, because in the last maybe 5-7 years, there has been a lot of work in what people call the memory store. Now, there is an agreement or disagreement whether it is the fourth passive element that was missing out of the passives that we have, which is a resistor, capacitor, inductor. So about 2011, there were all kinds of publications that said, no, there is, in fact, a switch that exists. And this switch is much faster than the other switches because it is based on the ionic displacement. So it creates a current, and as a matter of fact, it turns on at a much lower voltage, and the speed is much higher, and the on-to-off resistance can be like 10 to the 7th. And the speed can be below a nanosecond. And those have been developed. They have been, of course, there are spintronic memory stores, and there are ferroelectric memory stores also since then, and they are all very good, as a matter of fact, because at least for our application, they do exactly what we want, which is very high speed, and just one resistance to worry about. And they operate in much lower, they require much less power. So this is how they create them. The person who is working on that is going to come and give us a lecture here from UC Santa Barbara. He was with HP to talk about these memory stores. And they are using primarily for RAM, not for high frequencies. The reason those resistive switches are used today is for storage and for processing for RAM primarily. And they've measured their properties. So this is how this switch works. This is important to us for where we operate in the RF on the front end. So it's important to see that that rise time is very fast. That's all that we need. And you can see how you can develop them on a grid. And that makes it also easy to access it if you need a number of them. So the idea was, therefore, to use something like this, which people also are using. And then there is our colleague here, Leo. Where is Leo? He has a project that is working on this primarily idea. But people have been thinking about this for analog, hybrid analog, digital. The idea was that if you really use a real-time matching network, you can really move, and then you use not just a filter but a correlator. Then correlators can give you the signal out of noise primarily. And this way, instead of needing all of these phased arrays, where you have a phase shifter, and of course the power divider, the RF source, and the whole thing, and the receive end is equally complex. And that may be an antenna that somebody made that. So I like the picture and I put it there. You can have something like that. So if you could really get information, the bit information out of your antenna, and if you then use processing at the analog, you have a software that allows you to be able to extract information from the bits you get from every antenna. And if each of the antennas has a characteristic that you can differentiate what comes from every antenna, why would you need then a phased array? You could have all of your software to do the work. Now, all of this is the future. I'm not suggesting that the work has been done. I'm only suggesting some directions, and I'm posing a number of questions. But I think at the end, personally, I believe that there is an opportunity, there is a possibility of totally reducing the RF front end by totally throwing out a lot of the things we have kept in there. Now, if that were to be the case, then you can think beyond the traditional, and not only think about neuromorphic computing, and we'll have somebody who's going to come here to talk to us about neuromorphic computing and how they try to replicate the way the brain works. And as a matter of fact, there are all kinds of different suggestions because, well, we know more now about how the brain works, but we do not exactly know how the brain works. We just have more information. And a lot of people would like to see, for example, they try in neuromorphic computing to replicate the way the brain works because the brain requires very little energy, as opposed to the energy we use for a microprocessor. As a matter of fact, I wanted to ask you, do you know how many transistors do we have, CMOS devices? In the X iPhone, how many you think? How? Yes, over 2 billion. Do you think we operate all of them? If we were to operate all of them, then the iPhone would glow in the dark. So that is called the dark silicon problem, all right? We just cannot operate all of them. They're all there for all kinds of reasons. Many of them don't work. Maybe that's another reason. And not all of them are power-fed. So there is a problem. Maybe we can put lots of them together, but don't believe that we operate all of them as they are this close together. Not on silicon, not today. So people are trying to think on how the brain works. What is the brain has fewer neurons, but the brain does not as fast because a lot of the processes are chemical or thermal. But there's things that none of the machines we have created can do. And so it's important for those who work in this area to understand more. And so they, in this particular approach, they have digital communications, high-speed bus, for example, that is equivalent to axons. The neurons are similar to a microcircuit with 10, for example, that corresponds to 10 to the 5th neurons. One neuron can be about 500 transistors, and then you have the interconnects. And then they're trying on the basis of that to create, and of course it's not necessarily Boolean algebra that they're using for computing, is something different, but there is a very interesting area, not mine. However, in this one, I wanted to show you there was another interesting, where the neurogrid, for example, that can have all kinds of devices, is practically this. And then you have this, where it's the neurons practically. So that's what is called here the neurocore. It's something like that. It's this. And then, of course, then you have all other devices like neurons that operate like a neuron. There are some ideas about neuromorphic computing. If you want to read something, it's very interesting on how people have been really stimulated by how the brain works, and they are trying to think how far we can go in replicating some of these functions, but in electronic domain. And with that, I wanted to say the following, which is going to be very important to all of us here in the university. We cannot foresee or expect this future without rethinking the way we teach you about electronics. And as the future changes, as the present changes very fast, and the future comes to us a lot faster than we think. Also, we have many more new tools that come and become available. We have new topics and areas that become important, and it is critical for you to become interested in learning about those things and to try to find the opportunity that now your students to really try to bridge out and look into these new tools and learn more about how the brain works, learn more a little bit about biology. It's amazing. I was prevented from learning biology because the last time I had biology was in my senior class in high school. And I hated it because it was all classification of plants and animals. And it was not my thing. But I have to tell you, I came today to believe, now I have to learn now. Teach the old dog new tricks, all right? So you can. I mean, in this age, I don't have the ability to absorb, neither the years, cannot see so many years ahead of me like you have, to be able to see yourselves trying to do a lot more similar to what nature has done. And I suggest that you pay attention to your chemistry, you pay attention to your biology. For those of you who never had a biology class, please do not graduate without getting one. It's going to be very important. So with that, I'm at the end, and I wanted to thank you. Or ask any questions you may have. Questions are okay. There are no dumb questions, there are dumb answers. So I have to worry. No, yes?
Actually, two questions. I like the discussion of the front end, and then two other things which I think come into play. To do the RF side, then you have the optical side.
Yes.
How you connect the RF and optical system is, I think, there's a lot to be done in a positive way, because that's not very efficiently done.
Yes.